Okay, so now we will also look at the application of derivative in order to find local maxima or local minima. What we know, what we have seen is that if a function attains a local extremum at a point C, and if f is differentiable, then that point C is called a critical point. And if f is differentiable at that point, then we have seen that f prime of C is equal to 0. So, now intuitively look at a function which is having a maximum. That means, from the left hand side it is going to be an increasing function, and from the right hand side this is going to be a decreasing function. That is intuitively true. If one thing is that if this happens, then definitely it is going to be local maximum. It increases, then after this it decreases, then this is going to be a local maximum. Similarly, if it decrease and then on the right hand side it is increasing, like decreases, and on the right hand side it is increases. So, obviously, this one would safely say that this point is the local minimum. So, let us try to prove this. This is the first derivative test for local maximum or local minimum, that is the first derivative. For local extremum. So, now let C be a critical point, and f is differentiable on C minus delta to C plus delta, except possibly by C, except C, I mean in this interval, this is C. So, here is some delta C plus delta to C minus delta, f is a differentiable function, and given to you is that f prime of x is greater than 0 for all x belongs to C minus of delta to C, and f prime of x is less than 0 for all x belongs to C to C plus delta, then f has local maximum at C. Similarly, if f prime of x is less than 0 for all x belongs to C minus delta to C, and f prime of x is greater than 0 for all x belongs to C to C plus delta, then f has local minimum at C. So, that means what it is saying that on this f, suppose we want to prove this, then on this interval f is an increasing function, and on this interval f is a decreasing function, though intuitively this is going to have the local maximum at C. So, f is increasing on C minus delta to C. We want to say so that f of C is greater or equal to, want to show f of C is greater or equal to f of x for x belongs to C minus delta to C plus. Okay. So, in some neighborhood of C, f of C is greater or equal to f of x. So, f is increasing on the left hand side of this. Now, you take a x 1 belongs to C minus delta to C. So, wherever you take your x 1, you will always find a x. So, we can find x belongs to x 1 and C. There will be, in fact, there will be an interval lying between x 1 and C, the entire interval. So, now if x belongs to x 1 and C, this is, then f of x 1, this is going to be less than f of x, because both x and x 1 are in C minus delta to C. So, this is true for all x belonging to x 1 C. This will imply that f of x 1 is lesser equal to limit x goes to C minus f of x. Now, f is a continuous function, and let me, this is very important, f continuous on I and C belongs to I be a critical point. Now, this is equal to f of C, as f is a continuous function. So, therefore, whatever point we take on the left hand side of to C, f C is greater or equal to f of x. Now, similarly, if you take x 2 belongs to C to C plus delta, then consider, then for there will be C 2 x 2, this is going to be a non-empty open interval, and if x belongs to this, this will imply that f of x 2, this is, in this it is decreasing. So, this is lesser equal to f of x, similarly the limit which goes to f of C. So, f of C is greater or equal to f. So, in any of this case, f of C is greater or equal to f of x for all x belongs to C minus delta to C plus delta. So, this proves that if you have a continuous function and C is a critical point, on the left hand side of the critical point, if f is increasing and on the right hand side it is decreasing, then f is going to have the local maximum. Similarly, we can prove that if on the left hand side it is decreasing and on the right hand side it is increasing, then f is going to have local minimum. There is a word of caution that the converse of this may not be true, that if f has a local minimum, then not necessarily that on the left hand side the function is going to be an increasing function, decreasing function, and on the right hand side it is going to be an increasing function. That may not be true. So, for example, you can look at the function f of x is equal to minus of x sine 1 by x square. Then at you can show that this is going to be a differentiable function, we have shown that, and so f of 0 is going to be 0. So, this is 0, x is equal to 0, x not equal to 0. So, now if you want to look at the decreasing, you can always find, however, you can see that if your x is equal to 1 by n pi, then what you are going to get is that f of 1 by n pi is going to be 0. And if you take x to be 1 by 2n plus 1 pi by 2, then this is going to give you a negative number, and because this is going to get 1, and here you will always get 0. How for n large you are always going to get 0 inside any small neighborhood of 0. Nevertheless, so do not worry about it, but it is behavior is such that it is not necessarily true that if it has a local here 0 is a local maximum, as you can see that everything is negative. So, 0 is going to be the local maximum, but there is no, it oscillates so much that you cannot say that nowhere it is going to be increasing or decreasing. Every small interval you are going to take around 0, there will always the function is going to oscillate. So, that shows that the converse may not be true. So, however, if one remark, if f prime does not change sign, then f has no local extremum. So, it does not change sign means it can either be 0 or, so that means what? If I look at c minus delta, c plus delta, in this there is an interval around c in which f retains its sign. That means either f is f prime is 0 or f prime is positive in this entire interval, or f prime is negative in this interval. This means does not change sign means there are three possibility: f prime of x is equal to 0 for all x, or belongs to this c minus delta to c plus delta. F prime of x is strictly positive, or third part on this interval, f prime of x is strictly negative. Okay. So, now if f prime of x, if this is 0 on this interval, then f is constant. So, this is not the local maximum or minimum, what we will say. Now, if f prime of x is strictly positive, then f is an increasing function. So, f, this one will say that f is an increasing function. If it is an increasing function, so definitely whatever the value f of c is, so on c plus delta all this value they will be greater than this, and on this all this value will be less than this. So, it has no local extremum. Similarly, here f is decreasing. So, definitely here decreasing means all this value on c minus delta will be greater than f of c, and all these values on c to c plus delta will be less than f of c. So, there is no local extremum there. So, if it does not change the sign, then we can say that there is no local extremum. So, naturally one would like to ask that suppose I have a function f which is differentiable and f prime of c is equal to 0. So, now when can I say that this c is going to have f is going to have local maximum at this point c? We need some condition, just f prime of c is not going to tell that whether it is going to have local maximum or local minimum. So, what we need to check that whether it is increasing and decreasing or increasing to conclude about the local maximum and minimum. So, here is one result which will be very handy, that let C belongs to A B and f prime of C is equal to 0, 0. If f is twice differentiable and f double prime of C is strictly less than 0, then f has local maximum at C. Similarly, with all this condition, if f double prime of C is greater than 0, then f has local minimum at C. Okay. So, how does one prove this? Now, what is f double prime? It is given that f is twice differentiable, therefore, f double prime C will exist. That means, this is limit x goes to C, f prime of x minus of f of C divided by x minus of C. Now, f prime of C is given to be 0. So, this is equal to limit x goes to C, f prime of x divided by x minus of C. Okay. Now, take your left hand limit, that means consider x belongs to C minus delta to C. That in this case, the sign of x minus C is going to be negative. So, now, limit x minus C minus f prime of x divided by x minus of C, this is equal to f double prime of C, because this exists and which is given to be negative. Now, this is negative, this denominator is always negative. So, what do you get? You get that f prime has to be a positive number, otherwise this is cannot be negative, because denominator is negative. This will imply that f prime of x is positive for x belongs to C minus delta to C. So, f is on the left hand side, it is f prime of x 0. Similarly, if you look at C to C plus delta, then limit x goes to C plus f prime of x by x minus of C, which is equal to f double prime of C, which is negative. Now, x minus C is always a positive number. Therefore, the ratio is going to a negative number. That means what? That means essentially that f prime of x, this is going to be a negative number. That means, on the right hand side neighborhood, f prime is negative, and on the left hand side f prime is positive. Therefore, this is increasing by the previous result, f has local maximum at C. Exactly the same argument is going to be true for if f double prime C is positive. Many a times this is going to be very handy to check if f is twice differentiable, then to check that whether this has local maximum or local minimum. Let us see it with an example, concrete example. Let me take that f of x, this is equal to 12 x minus of x cube. Okay. So, now f prime of x, this is equal to 12 minus 3 x square, which if I take 3 common, then 4 minus of x square. Now, f prime of x, this is equal to 0 if and only if x is equal to plus or minus 2, right. So, now let us try to look at the sign of f prime. So, when x is less than minus 2, then x square is going to be bigger than 4. Therefore, f prime of x is going to be negative. So, f decreasing, and if it is minus 2 less than x less than 2, then f prime of x is definitely positive, because x square will be less than 4. So, f increasing, and if x is greater than 2, f prime again is less than 0, f decreasing. So, you see at minus 2 on this side, f is a decreasing function, and on the right hand side it is an increasing function. So, at f has local minimum at minus 2. Now, in this 2 on this interval, f is increasing, and on the right hand side it is decreasing. So, on in this interval f has local maximum at 2. Now, the same problem, let us try to do it by using our second derivative test, because here it is a polynomial. So, it is twice differentiable. So, now if we approach the second test, then we need to check at double derivative at 2 and minus 2. Now, what is f double prime? F double prime of x is equal to 12. 12 is minus of 6 x. So, f double prime of 2, this is equal to minus 12 negative. So, it is going to have a local maximum. Now, f double prime of minus of 2 is equal to 12, which is positive. So, at minus negative 2, it is going to have a local minimum. So, this is very handy if one goes to the second derivative test. Sometimes we may find it quite hard to even compute the second derivative. In those cases, the first derivative test is going to, we need to look at the sign of f prime on the left hand interval and right hand interval. Depending on the situation, we are going to apply this test. And so, in the next application of this, we will see that how the derivative is going to help us to determine a curve in which way it is bending. That is what also we are going to see a beautiful application of derivative in the next lecture. Thank you.